Ready?
Yes, I am.
Okay, so welcome to the HPC Best Practices webinar series. The series is brought to you by the IDEAS Productivity Project with funds funded by the Exascale Computing Project. The series is also a collaboration that involves the U.S. Department of Energy computing facilities at the Argonne, Oak Ridge, and Lawrence Berkeley National Laboratories. I'm Osni Marquez from Berkeley, Ashley Barker from Oak Ridge, and I will be the hosts for today's webinar, Accelerating Numerical Software Libraries with Multi-Precision Algorithms. And the webinar will be presented by Hartwig Ernst from the Karlsruhe Institute of Technology and Piotr Luzak from the University of Tennessee. Hartwig obtained his PhD in mathematics at the Karlsruhe Institute of Technology and afterwards joined the Innovative Computing Laboratory at the University of Tennessee. He's author of the Magma Sparse open source software package, and he's the managing lead and developer of the Ginkgo numerical linear algebra library. He's the PI of the effort that focuses on the development of multi-precision numerics for exascale computing in the Exascale Computing Project. Piotr is a research assistant professor at the University of Tennessee and also a member of the Innovative Computing Laboratory. His mixed precision work goes back over 15 years. Currently, he serves as a co-PI for the XSDK project funded by the Exascale Computing Project. And one of the main goals of XSDK is to introduce mixed precision approaches to the software for exascale machines. More than 200 people signed up for this webinar. Let's see how many will show up. And all attendees have been muted. We'll be receiving questions through the WebEx chat and also the Google Doc. We have pasted those addresses, that address in the chat of WebEx. In the webinar, we'll have breaks so the speakers can respond to the questions that come in. With that, Hartwig, please take the podium.
Thank you, Osni, very much for this very nice introduction. So let me share my screen. I think that should work now. I guess you're now seeing my screen. If someone could reply, that would be awesome.
It's starting. I see the starting here. Let's see. Yes, good to go.
Perfect. Thank you very much for this very nice introduction. And we just have that very first slide that you actually also, you may have seen us at conferences, Peter and me, and just that you can kind of relate the picture to us. Yeah, it is a big honor to actually be presenting here in the BSSW IDEAS project. And myself, as Osni already mentioned, I'm leading the ECP multi-precision effort. And this is why I recently have a lot to deal with multi-precision algorithms. And Peter himself, he has a long track record of working on multi-precision algorithms. And he is probably also the one who is much closer to hardware. And therefore, I will give the word to him for starting off this webinar.
Okay, thank you, Hartwig. If you could skip to the next slide. In addition to a lot of algorithmic work that's been happening in the community, recently we've seen a lot of resurgence in interest in new hardware. And on this slide, I'm showing you some pieces of equipment that's been already released, and they are unlike anything else that we've seen in the past few decades. So on the right is this gigantic orange wafer from Cerebras. Might be familiar with where the entire area of the chip is devoted to floating point units. And for comparison, at the corner, it's the upscale image of the V100 GPU chip. On the left, we have the TPU, and on the upper right corner, the gray board is from the Graph Core, part of their IPU and the Colossus version 2. So what all these pieces of hardware have in common is that they introduced a lot of floating point computation, but in precisions that are not necessarily on IEEE, at least at the time that this hardware was released. So let's move to the next slide, Hartwig, please. So here is a little bit of deeper dive into precisions. So these are multiple generations of one particular type of hardware, the GPUs from NVIDIA. Just so not to clutter this slide, we chose the selection of the cards, and what we show is the years up on top, starting in 2007 when the CUDA was released, and then the next row we show all the names of the cards, and the next row shows the relative compute performance, when we don't actually show the gigaflops or teraflops values, but we show the difference between single and double precision and how it varied between different generations. And the last row shows the relative memory performance that shows how much faster the transfer of these particular floating point values will have depending on the hardware. And so you can see in the row with the relative compute performance, we have a very wide range of values and differences between different precisions. And as we get closer to a more modern hardware such as Pascal and Volta, we even have three different numbers. And so these numbers correspond now not just to single and double, but also to the half precision. And to make things even more complicated, at the very last entry in the corner, you see that there is a star next to 16 because the operations take place on a specialized hardware unit that NVIDIA calls tensor cores, and you see that visualized at the bottom of the slide, and that actually is performed in rounding in a higher precision than the input arguments. So the landscape definitely of floating point precision formats and floating point precision compute capabilities is very rich. Now, if you could move on to the next one, please. So the summary of this slide, if you are overwhelmed by the numbers, is that compute-bound applications show performance gains in lower precision that depend specifically on the hardware. So as you go from Volta, the difference is 16x, and if you go on Maxwell, the difference was 32x for half precision compute. If you, however, look at the memory-bound applications, which Hartwig will be talking about extensively, we can see that these numbers are much more architecture independent, because what really counts for memory-bound applications is the amount of actual bits that get transferred across the buses. So generally speaking, the floating point precision in 32 bits is twice as fast than 64 bits, and 16-bit arithmetic is about 4 times faster when you have to move it across the bus, across the memory hierarchy. So let's move to the next one and talk about more memory and compute, but now in a little bit of idealized view using the roofline model. So we can see that the double precision compute performance, again, that would depend on the architecture. So we don't really know. That's why there is this question mark that we put, and we don't know how much higher single precision is going to be, because that's a decision of the architects of the chip. However, on the left, we see the slope when we see the memory-bound portion of the roofline model, and in that section, we can almost be certain that it's just going to correspond to the number of bits, and so the difference is 2x. So the slope is 2x between double and single precision. So let's move to the next slide. We will be talking more about the floating point format. So this slide is borrowed as a courtesy from Ignacio Laguna, that did the IDEAS webinar number 34 and talked extensively about tools and techniques for floating point analysis. So many of this new hardware, they break with the IEEE 7.5 format, but they, roughly speaking, keep this format of a sign, exponent, and significant, sometimes also called a mantissa. represent the numbers. And if you look down at the bottom of the picture, in orange, we have this danger zone area where these formats run out of storage capacity, and we start dropping numbers either to 0 or making them some special values such as infinities. So let's move to the next slide where we talk a little bit more about the particular formats. So because there are so many of these formats, we have a way of encoding them. So this is what we show with all these formulas. So we compare 4 different storage formats: double precision FP64, single precision FP32, and half precision FP16. And something that was introduced and was not originally part of IEEE standard is the BF16 that is called by Google a brain float 16-bit format. And so the way we encode it is we start the FP for floating point and the number of bits for the exponent and significant. So the numbers have to add up to the number of bits minus the bit for the sign. And the two half precision formats, FP16 and BF16, they are similar because they are exactly the same amount of bits. However, they differ in the way they represent the exponent and the range of numbers that they can store. So the half precision format that was in IEEE since 2008 uses 5 bits for the exponent and 10 bits for the significant. Google, when they introduced a brain float format, they decided to keep the range of the single precision format. So you can look at the very bottom and see that the exponent uses 8 bits, just the same number of bits that the floating point 32-bit format. And so because of that, they can keep much of the range of the numbers. However, because they made that decision, they store much less bits in the significant, and so you can see the U value, which is the unit roundoff, is much greater for the brain float format. So that means that the accuracy of it is smaller, so that there will be more roundoff error in that format. So that kind of goes into the details of the format, and now I let Hartwig take over with the more details of numerical aspects of different formats. Go ahead, Hartwig.
Thank you, Peter. So as Peter mentions,
should we ask for questions?
Are there already any questions for Peter?
No questions so far. Please go ahead.
As Peter already mentioned, we can broadly say that the exponent kind of indicates the range of the values, and the length of the significand determines how accurate the values in that range can be represented. And obviously, the longer the significand is, so the more bits I have, the more accurate I can represent numbers and values in that range. Now, of course, if I now do computations with these floating point numbers, what happens is that I get some rounding effects. So I will get values that I cannot represent using my floating point format, and I have to round up or round down, and I will get rounding errors. And an important thing is that over a sequence of computations, these rounding effects accumulate. So just an example, here I have basically a sum over n values xi, and I do it in a certain floating point format. And in the worst case, what could happen is I would get the exact sum plus n times the unit roundoff. So that would be the worst case scenario, that every time I add another number, I add a unit, or I lose the accuracy of the unit roundoff. So that would be the worst case scenario. However, in reality, there are different effects that play in our favor. One is that we have stochastic effects. So this will likely not happen, but what will happen likely is that sometimes we round up and sometimes we round down. And we can say that on average, we will be off way better than with getting the error n times the roundoff. unit roundoff. Another thing is that if we compute on parallel systems, and this is what we usually have, the sum will not be computed in like a sequential fashion, but what we will do is we will have a blocking algorithm. So for example, we will have a tree-based sum computation. So I kind of try to visualize that on the right bottom. And this doesn't necessarily mean that I really have like a binary tree. So I have two atoms, then I form the sum and go up. But maybe I have on the lowest level, I always form the sums of a block of 10 elements or something like that. However, the overall effect still remains the same. So the round-off is reduced by this tree-based addition. Now, what we are looking into today is not necessarily only the sum of elements, but we want to look into what does it imply on our numerics. And specifically, we are focusing on linear system solves. So we assume we have a system AX equals B, and we will later look at the effects of rounding for this specific application. However, the insights that we gain carry over to a much broader group of algorithms. So if we look at a linear system AX equals B, this system has a condition number. So one speaks of the condition number of the system, and the condition number basically reflects how sensitive the solution X of the system is to changes in the right-hand side B. So if I have a very high condition number and I do a small perturbation to the right-hand side B, my solution will look totally different. Now, if I use a numerical method in a certain floating point format to solve that system, this can be a direct solver or an iterative solver, I introduce rounding effects. And these rounding effects are basically equivalent to doing a perturbation to the right-hand side B. So that means that if we have a very ill-conditioned system, so a high condition number, each of these rounding effects will have a pretty significant effect. And in the end, our solution will only have a certain accuracy. And that depends on the condition number and the floating point format that we use. And as a rule of thumb, we can say that the actual result accuracy will be, in the best case, the unit round-off times the system linear system's condition number. And if the solution can have at most that accuracy, also the relative residual will at most have that accuracy. And just to give you an example, so if we use double precision and we have a system with a condition number of 10 to the power of 10, which is not that uncommon, we will never get better than a relative residual accuracy of 10 to the power of -6. And this is a very, very important takeaway, I would say, because often you see calculations where they try to achieve enormous accuracy while using double precision or something like that, and the system is ill-conditioned, so they will never actually get there. So they will probably have an iterative solver breakdown that pretends to have fulfilled that accuracy, but if you then look at the backward error, it will not fulfill that accuracy. So let's actually take a little example. So I look at a system AX equal B with a condition number of A being 10 to the power of 4. And then I use a unit right-hand side and I run a solver in double precision. And the initial residual was 111. And after some iterations, in this case, it's 1,200 CG iterations, I get down to a residual of 10 to the power of -10. And so I have a relative residual improvement or a relative residual of 10 to the power of -12. So in this case, it perfectly fulfills that rule of thumb. This basically was expected. So now if we use software that uses templated precisions, and in this case I want to advertise the use of C++ libraries, you can easily switch the precision that is used for the arithmetic. So if you are interested in trying that out, we put a couple of examples into the Ginkgo linear algebra library, and down at the bottom of the slide you actually find the link to the exact file where this example is inside. And you only have to change the precision format that you use for the arithmetic in a single place. So this is a feature of C++ that is very powerful. So you template the precision. So if we now change from double precision to single precision, what happens? Well, we roughly run the same number of iterations, but we only get a residual improvement or a relative residual of 10 to the power of -4. So while this is roughly, again, according to the rule of thumb, we have seen, obviously, we can't get any higher accuracy using single precision. What is interesting, though, is, or let's first look at what is happening. So here what you see is the actual residual behavior over the iterations. And while the single precision CG stagnates at some point, so we don't get any higher accuracy, the double precision residual converges down to the accuracy of almost 10 to the power of -10. What is interesting, though, even though we ran roughly the same number of iterations, is that the single precision CG was roughly 10% faster. And where does that speed up come from? That speed up comes from, and we can be sure here, from the reduced memory access. So CG and also that linear system is being sparse, is completely memory bound. And if we are using single precision throughout the algorithm, we just transfer less data. And that is something that is very useful. So we do know, OK, using single precision, we will not converge to high accuracy, but we can do the computations faster. Why is it not a speed up of 2? Like we have seen the bandwidth, basically if single precision has half the number of bits than double precision, you could expect a factor of 2. Well, we don't get that because on the one hand, a sparse matrix, like in this case, is stored in CSR format. And CSR does not only store the values, but only has to store the location information, and that is integers. And that is, of course, not changed when going from double to precision to single precision. So we don't exactly get the factor of 2, but we do see some speed up. Now, let's look at a system that is very ill-conditioned, and this is actually the Apache 2 matrix from Sweet Sparse Matrix Collection. And there this matrix has roughly a condition number of 10 to the power of 7, which is almost exactly the unit round-off of single precision. And what we see is that in the double precision solver invocation, we still get a relative residual of 10 to the power of -9, which is according to the expectation. However, if we run it in single precision, we basically have like no improvement. So the condition number is within the range of the inverted unit round-off, so we don't see any improvement. So takeaway at this point, the rule of thumb tells us that the relative residual accuracy is the unit round-off times the linear system's condition number. For ill-conditioned problems, we need high precision to get any results or any high accuracy results. And only if the problem is well-conditioned and a low accuracy solution is acceptable, then we can also use a low precision format, and we will be likely faster. And the takeaway from the software implementation side is that templating the precision formats, especially the value type, that allows to quickly switch between formats. And that can be very, very useful when developing software packages, because maybe in the beginning you don't know which kind of systems you are targeting, and you can later on see whether moving to single precision still gives you the result accuracy that you needed. And there are a couple of popular software packages out there, not only Ginkgo, but also Cocos kernels, Trilinos, and so on, that template the precision and that are based on C++ and very useful in that respect. Questions at that point? Maybe.
Yes, there's one here, actually 3. Would it help to run most iterations with a single precision, then finally converge with higher precision?
Yes or no, it depends on the solver. So that is a very important research area. If you have a solver like a stationary method, like Jacobi iterations, then it makes sense to start with low precision, like for example, single precision or even lower, and then successively increase the precision format. So if the person who asked the question is interested in that, I can also point him to a paper. However, with Krylov solver, it's interestingly the other way around. So it's important that you start with high precision, and then over the iterations, when you start getting closer to the convergence, then you can switch to lower precision. It's counterintuitive and very interesting, and it's, I would say, very recent research. And I can also point the person who asked the question to literature on that topic.
And I think going back to the example that you showed, Hartwig, another question: Do you block the system?
Do I block the system in terms of forming small dense blocks inside the matrix? No, this is just a CSR matrix. I store individual values, if that is the question.
I think that was the question. Then another one: why not twice as fast?
Why not twice as fast? Yeah. So as I mentioned, one reason for that is that we need to store the location information in case we have a sparse matrix. So basically, it is in this case, the row pointer and the column index. So that is needed for the CSR format. And the second reason is that even though the solver is for sure memory bound, it is not that all operations are affected the same way by reduced data volume. So for example, if we have a reduction, and a reduction is an essential component of every Krylov solver like CG, it will not be a factor of 2 if I run the reduction with lower precision values, like moving from double to single. And that is because for these operations, we can't leverage the full bandwidth, but we have to give something away because it's basically an asymmetric operation where not all the compute units, in this case is a GPU, are used the same way. So if this was run in a sequential fashion on a CPU, maybe we would get closer to a speed up of 2.
All right. So one question that just came in. Could you contrast the C++ precision templates with Julia's multiple dispatch model?
I think that goes beyond my knowledge. Maybe Peter can say something on that. I'm not too familiar with Julia's model, to be honest. Is it also static polymorphism, or is it dynamic? So is it basically, is the kernel chosen during runtime or during compile time? I wouldn't know that.
Well, with the Julia's inference, I'm not an expert, but I can mention a few things. So definitely the C++ templates are much less powerful than the Julia's type, both inference and multi-dispatch. So you can definitely achieve way more sophistication with the Julia type system. But with a lot of software that we write, C++ is prerequisite. So we have to kind of work with the minimum common denominator of the functionality.
Thank you, Peter.
We can take that maybe more details later in the write-up, so we don't take too much time for those.
Okay. Do you think we should? There is another question here. Should we delay, or would like to take it now?
Maybe give it to me, and I will see whether I can answer it quick.
So I have read that newer CPUs convert single precision to double precision because hardware for double precision is faster than single precision. Can you comment on that?
I haven't heard about that. Maybe Peter, you can do a quick research on that, or if you know the answer right away, speak up. Otherwise, I think we delay that for the end of the meeting. I think that.
So definitely there is hardware where the IBM Blue Gene systems at some point did not feature a single floating point. Everything was just cast to double precision. So yes, there are oddities like that, but most of the time, single precision is expected to be faster both in transfers and in compute.
So I suggest we continue. There are some more questions, but I'll be.
Yeah, let's continue.
Yeah.
Okay. So now the question is, if we have a nil condition system, so we ended up with this one, Apache 2 from Sweet Sparse, and we have seen that we cannot really gain anything with single precision simply because the condition number is so high that running a solver, an iterative solver, would not bring us any improvement. Now the question is, can we still somehow leverage single precision to solve a system like with this condition number versus just using double precision throughout the complete algorithm? And for this, some background about the idea of preconditioning is needed. So the general idea of preconditioning is to instead solve a system AX equals B, like here, we want to solve a system A tilde X equals B that has a better or a lower condition number. And how do we get there? Basically, we multiply from the left, for left from preconditioning, a matrix P to that system, or P minus 1, where P minus 1 is a rough approximation to the inverse of the system A. So that is basically the idea of preconditioning. We try to approximate the inverse of the system matrix and multiply that to the system. Now, obviously, you can see if P minus 1 was the exact inverse of A, then we would have the solution right away, because then P minus 1A would be the identity matrix. On the right-hand side, we would have A minus 1B. But that is usually not the case. That is too expensive. That doesn't bring us anywhere. And in most cases, P is only a rough approximation. So that being said, if P is only a rough approximation of the system inverse, it is a fair question, why should we use the preconditioner in full precision, like in high precision? Let's assume the full precision is double precision. The question is, if we have a preconditioner that is only a rough approximation of the inverse, why should we use that in full precision? Maybe we can use lower precision. And that is a pretty attractive idea. And I want to give you a short example on how that works. So assume we have a Jacobi preconditioner. So the Jacobi preconditioner is basically the inverted diagonal of your matrix. And now a more sophisticated Jacobi preconditioner is the block Jacobi. And in this case, you do not only consider the main diagonal, but you consider a diagonal of blocks. And you invert this block diagonal. And each of these small blocks obviously corresponds to a small linear system. And as you can imagine, the bigger the blocks are, the stronger is your preconditioner, or the more accurate is the preconditioner. Assume the blocks are the complete matrix, then you have the exact inverse. Well, in reality, this is way too expensive, and one usually has very small blocks, or blocks of moderate size, maybe something like 20 at most. Basically, this block Jacobi preconditioner ignores all the entries that are outside the main diagonal. So it's only a rough approximation. And your question is, why should we use that in high precision? And now the idea is, let's use it in low precision. Now, in general, the idea of using that in low precision is perfectly fine, except for if we also apply it in low precision, so we do the computations in low precision, then we have a non-constant preconditioner. Unfortunately, I don't have the time to go into detail there, but I'm happy to explain that afterwards if someone is interested. However, we have seen that these algorithms are all memory bound. So in the end, it doesn't really matter in which format we do the computations. It all matters in which format we transfer the data between main memory and processing units, or in between processors. So the idea is to basically say, okay, we maybe still compute in high precision, saying double precision, but we decouple the memory precision, we convert it into a lower precision, and then we write it to memory or we read it from memory. So all the memory operations use a lower precision, and only the operations are still using high precision. By doing so, we basically we reduce the data that we transfer between the memory and the processing units, so we will get all the speed up that we want. At the same time, we have the high precision in the operation, so we apply a high precision preconditioner, only it is, in broad words, rounded. And by doing so, we keep the preconditioner a constant operator. So let me give you some details about what we are exactly doing. So we look at the block Jacobi preconditioner as a set of small linear systems. And now we want to store these small blocks in lower precision. And of course, we cannot just choose a lower precision format because, as we have just seen, if we use a format that is too small to actually either give us any accuracy, or it is too small in terms of the range of the exponent, we will not get anything. So the whole algorithm will break down. So like in the situation where we wanted to solve a linear system, we have to look at each block, look at the condition number of the small block, and look at the exponent range. And then, depending on the exponent range, the condition number, and the question, how much accuracy do we want from our preconditioner, like in the linear system solve, we can select a storage format. And here on the right top, I basically propose a couple of storage formats. So this down here, of course, is double precision, and then we have different other options, single precision, or some other precisions. Basically, you could make up any precision format where you have that the exponent fits your data range, the condition number is well covered, and you still get the accuracy of your preconditioner that you want. A quick check on what implications that has. Of course, we preserve regularity by checking the exponent range and the condition number. And we can also select how much accuracy do we want from our preconditioner. We do the computations in double precision, so we have still a constant operator. And we have a couple of drawbacks. So we have some overhead from the precision detection because we have to compute the condition number. And we also have to store the information in which precision is that block stored, because we later on have to reconvert that to double precision again. And of course, the speedups are very problem dependent. And what do I mean by that? So let's look at the Apache 2 system that we looked at previously. For this case, if we use a block Jacobi preconditioner and all blocks have the size of 16, we see that we can store all the blocks in half precision. So basically, this is on the left-hand side, you see the block distribution. This is 100% of the blocks, and I can store all the blocks in half precision. This is not always the case. So if I look at a different matrix, I have to store some of the blocks in double precision because they have a high condition number, and some of the blocks I can store them in a single, and only very few in half precision. If we look at all the SPD matrices from the Swiss sparse matrix collection, we see that it's all over the place. So for some of the cases, we can store all blocks in half precision, and some we need double, sometimes single. In very few blocks, we actually see that we have these awkward precisions that I denoted here on the top. And that is also an interesting information. So it looks like the IEEE standard is pretty strong in terms of covering problems. Or in other words, if I have a system with a certain condition number, I can kind of expect what the values, in which range the values lie. So it's very uncommon that I need a very long exponent and a very short significand. So you can expect that depending on how many blocks I can store in which format, I will have different speedups. So let's look back at our problem, the Apache 2 problem. Previously, we got a good residual in the double precision case. And now we couldn't solve that problem using single precision. Now what we now do is we compare the double precision CG solver with the double precision preconditioner against the double precision CG solver but a mixed precision preconditioner. So we store the blocks in lower precision. And what we can see is that we achieve the same residual accuracy. We have pretty much the same iteration count. So in fact, we need a few less, but that is some lucky rounding, I would say. But what we see is that we have roughly 16% runtime improvement. Now, you may argue that that is quite a lot of effort for getting 16%, but 16% are quite a bit if we look at sparse linear system solves. And the nice part is we have that code production ready inside the Ginkgo library. So basically, if I use Ginkgo and I have a CG solver with a certain stopping criterion and a preconditioner, block Jacobi with block size 16, I only have to add these two lines to my code, and I will get the 16% performance improvement for the Apache 2 system. For another system, of course, it might be a totally different performance improvement. That, of course, depends on the system. if you want to look at that code here, down here is again the link where you find that. And if we look at all the matrices from the sweet sparse matrix collection, you see in this figure, the red dots are the iterations, and this is here the speed up. So basically, the iteration count is in almost all cases the same, and the time is usually 10 to 20% above the one. So this means we get 10 to 20%, or let's say 10% speed up, something like that. In some cases, some higher speed up. And then there are a few cases where we have negative speed up for the iteration count. So that means I need a lot more iterations if I do the adaptive precision block Jacobi instead of the double precision block Jacobi. And the reason for that is that my block Jacobi preconditioner has a very high accuracy. So for example, it could be that these matrices are block diagonal systems. And then the block Jacobi preconditioner is the exact inverse. And of course, if I then reduce the precision of the inverse, I lose a lot of information. But this is a very rare case. In most cases, the iteration count stays the same, and we see some slight speed up. If you're interested in that, we also have the code in Ginkgo, and we also have an artifact evaluation where you can look up all these results here that I'm presenting. Now, takeaway at this point. We can use a low precision preconditioner to accelerate iterative solvers. We still get high accuracy of the solution if we are careful inside the preconditioner that we adapt the format to the requirements of the system. So that is a big possibility. Second takeaway is if we have memory-bound preconditioners, and that is almost always the case in sparse linear algebra, we should decouple the arithmetic or the arithmetic precision from the memory precision, because then we still get all the runtime savings from the less memory transfers, but we preserve the preconditioner being a constant preconditioner. And if we now continue that thought, if we want to get a lot of performance benefits, we should try to shift most of our work to the low precision preconditioner and only have a very lightweight outer solver. At this point, I again want to do a quick break and see whether there are any questions.
Actually, there are a bunch here, but I suggest you continue and then you
okay.
add. Yes.
Okay, let's try. So if we stay at that thought, we want to increase the performance benefits by shifting most of the work to the low precision preconditioner. Well, there's a very smart way of doing that, and that is the mixed precision iterative refinement. So iterative refinement basically solves an error correction equation. And the idea in mixed precision iterative refinement is to solve the error correction system in low precision and only do the outer iteration, like the residual computation, the update of the solution approximation, and the check whether we have fulfilled the tolerance. Only these operations are done in high precision. The most expensive part, solving the linear system AC equals R, is done in low precision. A good reference, if you want to learn about that, is Nick Hyung's book, Accuracy and Stability of Numerical Algorithms. And I also want to point you to a very nice MATLAB package that is written by Sri, a student from Nick, and there you can try out mixed precision iterative refinement algorithms, like a lot different combinations using either iterative inner solvers or direct inner solvers. Now, if we do that for our system, on the left-hand side, we have double precision iterative refinement. On the right-hand side, mixed precision iterative refinement. Also for the system with the condition number 10 to the power of 4, we get in both cases a relative residual of 10 to the power of minus 14. And this is exactly what we want. We have the same number of mixed precision iterative refinement counts loops, so 18 in this case. However, we are again about 16% faster if we use the inner precision of being single instead of double. So on the right-hand side, the mixed precision is roughly 16% faster than the plain double precision iterative refinement. Now, the nice thing about iterative refinement is, Yeah, I should probably mention some additional references on that. We are sure not the first ones who have discovered that. So there's a long history of using mixed precision iterative refinement also for sparse systems. And here I'm going to list just a few papers. And one important takeaway from all these papers is all these iterative refinement methods using sparse inner solves, they are all bandwidth bound. And basically, the performance gains will always relate to the bandwidth savings. So that is an important takeaway for sparse linear algebra. It's a good and a bad news. A good news is we will probably not be able to achieve a factor of 16 and in speed up. If we move from double precision to single precision, we will always remain smaller than 2. The good news is that it is architecture independent, more or less. There may be some variations, but in general, it is mostly architecture independent. Mixed precision iterative refinement and in general mixed precision iterative sparse linear system solves are available in different libraries. I just mentioned a couple down here: Ginkgo Hyper, Cocos Kernels, Magma, Petsy, and Trilinos. All packages that are well established in the community and that are very powerful in providing mixed precision sparse linear system solvers. Now, the nice thing about mixed precision iterative refinement is that it doesn't stop with linear systems, but you can also apply it to eigenvalue problems. And with that, I hand over back to Peter.
Yes, thank you very much. So this is just a few slides to show you how this mixed precision techniques would apply in eigenvalue systems that both deliver accurate eigenvalues as well as eigenvectors. So this is a work by our colleagues in Japan from about 2 years ago, and this is just a gist of the algorithm that I'm showing here because it's extremely simple. So on the input, we're getting a low precision matrix and its estimated eigenvectors that we can do in low precision much faster than we can do it in double. And on the output, we will get refined and higher precision both eigenvalues and eigenvectors. We will also get an estimate of the error that we incurred during the computation. So one thing to notice on both line 1 and line 2, the eigenvector matrix X is not square. It has a dimension n by l. That means that the algorithm works on just a subspace of eigenvectors. So the general method is shown below in steps 4 to 10, and let's take a look how this method behaves when we actually run it on a sample system so this is a system of 200 by 200 entries, and in the system we have 200 eigenvalues that we are refining at the same time. So we start with the single precision. So you see 200 lines starting on the left at 10 to the minus 6. And then as the algorithm runs and we proceed with one iteration after another, we refine it in double precision and reach 10 to the minus 16 and double precision accuracy. So because the system has 200 eigenvalues, and we are refining all 200 of them, we don't really have the problem of getting stuck with one subspace and some of the eigenvalues not being refined very well. But this is beyond the scope of this presentation. I just want to mention it, that could be a problem. Another issue with the eigenvalue problem is, of course, the the clustering of the eigenvalues. Again, we're not going to dive into that. So yes, if we can move into the next slide, where I'm going to look at the same algorithm that we started with for refining the eigenvalues, but now I'm just going to calculate the relative cost of refining these eigenvalues. So if I look at particularly lines 4, 5, and 10, these are lines that contain matrix multiplies that are of the size of the system that we're refining, so they are large. And if we compute some of those multiplies are symmetric, so we end up with 7n cubed number of flops for every iteration. So unless we were able to recoup enough of savings in the first part where we generated the low precision eigenvalues, we will not be able to benefit computationally from this routine unless we can converge very, very quickly. So this is an example when we can do an refinement for a nonlinear system for eigenvalue problems, but we have to be very careful about both numerical issues and the issues with computational complexity. So that would be it. I think that we're going to do the summary. Harvey, can you please summarize?
Yeah. So as on this last section on mixed precision iterative refinement, we have seen it's a very powerful strategy to accelerate linear solves. We can use direct and iterative inner solvers, and it is useful for both sparse systems and dense systems. We didn't really talk about dense systems today, but I think this is much more well known. So especially Nikayam and Jack Dongara did a lot of work in this area. Mixed precision iterative refinement can also be used for eigenvalue problems, as you have seen just in this last slide. However, all the performance benefits, they depend on the problem and the hardware capabilities, and it's not easy to say upfront how big the savings will be or whether there at all will be any savings. And with that, we want to reference a couple of papers here and also suggest some papers for further reading. So all these are kind of papers that have worked on this area, and either we use them inside this presentation or they are closely related and worth a read. And now we thank for your attention, and I think now we are coming to the questions.
Yes, thank you, Hartwig. So going back to the some of the examples you showed, so would it not be fairer to compare speeds asking for only a single precision residuum?
Can you please repeat your question?
Would it not be fairer to compare speeds asking for only a single precision residuum?
Only a single precision residual.
Yeah.
So if you're happy with the residual and single precision, so also the accuracy that that is possible with single precision, I guess you should always use a single precision algorithm. So if you're happy with what a single precision solver gives you, then it's always the better choice. And then it depends on whether it's memory or compute-bound algorithm. And for a memory-bound algorithm, you should, in the best case, get something closer to a factor of 2, if I understood your question.
Yeah, I think that's it, unless the participant elaborates later. Okay, so another question here. Since with a single precision, single precision stagnates, you can get underflows, etc., which can raise traps and other things. Could you comment on that?
Yes. So I guess this is relating to the slide where I showed the convergence of the double precision solver and the single precision solver, this one. And yes, it is possible that using single precision, we, for example, run into an overflow or an underflow. I don't consider these cases here. But of course, it's possible that this can happen. And of course, then it's not an option to first start with single precision and later on continue with double precision. If this is the graph the question asks about, yes, that is possible. If the question is towards the block-Jacobi preconditioner, well, basically what we do is we first compute the inverse in double precision, and then we decide whether we can store it in lower precision format.
Okay, another question here. Is there a lightweight multi-reduced precision C++ template library that you recommend? Do they use the old boost calls on CPUs?
So whether they're, again, a templated C++ library for?
Lightweight multi-reduced precision, a general question. It doesn't specify what the application would be.
I'm not exactly sure what the question is about.
Well, in my experience, let me start. For example, there is a library that is widely used and known called Eigen that includes the single and double and also half precision. And half precision on the CPU is actually implemented in software, but it has as an offload to NVIDIA GPUs. In CUDA, it uses a hardware acceleration, so it's relatively fast. And so that's one C++ library that I have experience with. And
so I'm probably now understand the question. So Ginkgo, Cocos kernels, and Trilinus, these three are definitely C++ libraries that template on the precision and that are ready to be used. The other ones also template, but they are not heavy C++, I would say. So Magma, for example, also templates the precision, and you can use the routines in single precision or in double precision, but it's not necessarily C++, the Magma library. Does that maybe answer the question?
Yes, it does. So there are no explicit templates for the routines like you have in Ginkgo or Trilinus. Magma just has different names that more look like C or Fortran names, and those names basically encode the precision. So it could be 64, 32, or 16 bits, and the routines are either regular for large matrices or for many small matrices in batch mode.
Like LAPACK. LAPACK also is available in different precisions, but you then always have the whatever SGEM or DGEM, and basically the first letter indicates which precision you're using. Maybe that answers the question.
I'll ask the participant to write in the Google Doc. So now another one here. Do you have the ability to add dot products in longer precision? We can show that this improved accuracy.
Yes. I guess that question is going towards the block-Jacobi preconditioning. No, we don't do that. So we do all the calculations in double precision, and then we write in probably lower precision if the system characteristics allow for that. And that is actually so kind of similar to what NVIDIA does in the tensor cores. They are also computing at least part of the computations inside the tensor cores use higher precision compared to what the output, the data format that is used for the output. So basically, they do it in hardware. We try to do it in software.
So another question here. Do you literally invert the blocks? Why not solve a system? Is there a specific reason for that?
Yeah.
It's common belief to never, in quotes, never invert the matrix.
Yes. So I have to say that these systems are pretty small. If they were big, I'm totally with you. You would never invert that system.
Okay.
The systems are small because the blocks are usually chosen to reflect the properties of the system matrix. So in many cases, the system matrix or many applications that use block-Jacobi preconditioning coming from finite element discretizations, and there you have multiple unknowns associated to an element. However, often this number is not big. It's maybe 6 or 8 or 12 or at most 20 or 30. So at that size, also the matrices are usually not ill-conditioned, and there it pays off inverting them, because inside the iterative solver, you apply the precondition over and over again in every iteration, and then it just pays off if you just have a matrix vector multiply versus 2 triangular solves. You can do that in batch mode. I totally agree with that, but in terms of performance, it pays off, and in terms of numerical accuracy, so we did experiments with the matrices that are available in the sweet sparse matrix collection, we did not see any differences. So for these small systems, it's reasonable to invert them.
Okay, so how do you choose the appropriate lower precision that we use? If that comes from experimenting, in reality...
No. It's not... Yeah, sorry.
Let me continue. If that comes from experimenting, in reality, would anyone run their applications multiple times to figure out which precision to use? And what about memory use if more than one precision is used?
So it's not experimenting. Excuse me, Osmir, that I interrupted you. It's
Sure,
not
no
experimenting. It is, so in the beginning, I showed you that I can use this rule of thumb to estimate how accurate I can get the solution of a linear system. So now if I have a small system matrix, that is the inverted diagonal block, then I can compute the condition number of that system. And what I can also do is I can see the exponent range of the numbers that are inside that block. Now I can say, for example, I do think that my preconditioner has or my block Jacobi preconditioner has an accuracy of, let's say, 10 minus 2. Then I do know the condition number of that system is 10 to the whatever 2. And I do know that I additionally want a solution accuracy of 2 digits. So I take 10 to the power of 4. And then I choose a precision format that has a unit roundoff of smaller than 10 to the power of minus 4. So this way I can make sure that the format that I'm using is preserving the regularity of the system, plus I get the accuracy of my preconditioner that I want.
Okay, so I have there are more questions here. Let's see, just to like to tell the participants that all these questions are going to be answered by the speakers, and we'll be sending the Q&A curated sometime to everybody sometime next week. But perhaps we have time here for a few more.
Sure,
more
I have time.
Here.
I'm not in a hurry.
No. For the numerical experiments, do you use parallelism?
Yes. So all these experiments that I showed today were conducted on a P100 GPU from NVIDIA. They also run on a Volta or any other GPU also from AMD. Ginkgo runs on AMD and NVIDIA GPUs. The experimental results will differ in the numbers, but they will not differ in terms of the performance benefits that you get from when moving from double to single, because the ratio between the bandwidths will remain the same.
So I see lots of people typing here. What is the difference between Ginkgo and Magma?
Ginkgo is C++, Magma is C.
All right.
Ginkgo is AMD plus NVIDIA, and Magma is starting AMD 2. But the sparse part of Magma hasn't been ported to AMD GPUs yet.
So instead of choosing between precision formats, wouldn't it be easier to normalize the data and store one additional scaling factor, even in double precision?
Yeah, that is a good idea. We have looked into that quite a bit. We were not yet successful, or let's say we did experiments. They were not as convincing as using different data formats. If you can show that it's more efficient, write a paper, be my guest. But we haven't had any success with that strategy.
Another question: how expensive is the function called Ginkgo precision _ reduction auto-detect?
I can, if you want, show you results. So basically, what happens is that additionally to inverting the systems, we also have to compute the condition number and decide on the system on the format that is used to store the system. So what I can say is that computing the condition number, you don't see that in the runtime. It's very interesting because the systems are so small. The inversion is Gaussian elimination with pivoting. It's so fast that again this operation is bandwidth bound. And whether additionally to the inversion you also compute the condition number, which is basically taking the norm of the original matrix and the norm of the inverted matrix and basically computing the ratio, dividing the two, you don't see that really in the runtime. If you also decide on the format to store the matrix, you have a little overhead that can be as much as 50%, but the whole thing is only done once. The whole thing is only done once in the generation of the precondition. And it pays off. So the numerical results included that.
Right. So going back to the roofline model, you showed that the low precision offers a speed up but reduces arithmetic intensity. Intensity. Do you want higher arithmetic intensity to a modern APC system? So how to maintain a balance?
Wait, so please, there are two different things. One is arithmetic intensity, and that is dependent on the algorithm. So the arithmetic intensity basically tells me, my algorithm, how many operations do I do per memory access. That is the arithmetic intensity that is tied to an algorithm. And on the other hand, I have the machine balance. And the machine balance is what my hardware can do. And a well-balanced machine basically has a good machine balance. So the ratio between the number of operations it can do in a certain time versus the number of memory accesses it can do is kind of the same. Now, what we see is that the machines get more and more imbalanced. A colleague of mine, Mark Gates from the University of Tennessee, he has just updated a very nice graph showing the machine balance of different architectures. And you can see a clear trend that on average, both is growing. So the arithmetic or the compute performance is growing and the memory performance is growing, but the compute performance is growing roughly 30% faster. So we get more and more imbalanced machines that provide more and more compute power while the memory access isn't growing that fast.
So final question here. As I said before, the speakers will go through all the questions later, and then we'll be sending the answers to everybody next week. Last question here. How important is basic language support for reduce the precision? How much time, for example, is wasted on conversions on CPUs?
So that is a valid question. So Magma, for example, they provide very good conversion routines that are also parallelized. It would be good to have native support for, or it is good and important to have native support for these conversions. In the best case, they are also parallelized. So you can call them, for example, on a GPU, and the conversion is done in parallel. Of course, there's some overhead associated to that, and I guess that depends on the implementation and the hardware. But if the question is how important it is, yes, it is important. If the overhead is too big, we don't gain anything by developing these precision algorithms.
Okay, with that, I think, so I'll go through the questions again, and you guys are going to take a look at them, and we'll send it to the participants. Okay, Hartwig and Piotr. So thank you very much. Ashley, could you give me, please, the sharing screen so I can announce the...
Yep, here we go.
Okay, so... So thank you all for participating. Please give us feedback so we can improve the series, and also for the speakers. I think that they would be happy. So I'd like to announce the next webinar in the series, which is going to be in June the 10th, and it's going to be on SQL, Introduction Best Practice. Remember, I think 2 or 3 webinars ago, the webinar focused on Cocos. So we are going to have a number of webinars in that kind of programming model. So the next one, then Introduction Best Practices for SQL. And the speaker will be Thomas Aponcourt from the Argonne Leadership Class Facility. And we are already open for registrations. Finally, so I'd like also to announce this the next panel in this series, Strategies for Working Remotely. This is going to be next week. I think it's May 21st. This is Thursday. from 3 to 4:30 p.m. East, making the transitions to virtual software teams. And then we have a number of speakers, J.J. Billings from Oak Ridge, Mark Gates from UTK, others, and moderators will be Ashley and Elaine from Sandia. So, and again, so the event is open there for registrations. The page is open for registrations. Thank you very much again. Ashley, if you have some final words.